Hello and welcome. Today we'll be solving Leetcode 130, surrounded regions. Now the question reads, you are given an M by N matrix called board containing the letters X and O. Capture regions that are surrounded. Okay, so connect. A cell is connected to adjacent cells horizontally or vertically. So for instance, with this cell here, we know it is connected to its neighbor's cells, either at the top, at the bottom, to the right, or to the left. Okay. Region. To form a region, connect every O cell. So in the instance of the cell I just marked, we know this right here can be a region, right? Because there are other O cells that are connected to it, right? And like we just mentioned, we know we can connect to neighbor cells by either going to the right, to the left, top, or bottom, right? And we can do that with these zeros here, and so that is essentially a region, right? Okay. The next is surround. The region is surrounded with X cells if you can connect the region with X cells and none of the region cells are on the edge of the board. Very important, that last part, that none of the region cells are on the edge of the board. Okay, so with going back to this example here, right, you can see that for each of the cells, either to the top, the down, the left, or the right, there's an X there, right? For this first one, we have an X at the top, to the left, or to the bottom. And if there is no X there, it needs to be connected to another O cell that is not at the edge, right? So then going off of that, we know that we cannot connect to this cell right here. Why? Because it's at the edge. Okay, so going on, it says to capture a surrounded region, replace all O's with X's in place within the original board. So after we're able to figure out what our regions are and like demarcate it in that way, we want to be able to just turn all of them into X's. So you see right here, all those O's become X's. Okay, so now the first time I saw this question, I guess like one of the first ideas that came to mind is obviously finding some way to move through our matrix board, and then when I find the O's, finding some sort of way to make sure that okay, they are either surrounded by O's that are not on the edges or by X's. And hopefully hearing it already, you can see how tedious that could be. That's a rather like complicated approach to practice. A different approach we could use, however, is to look around our edges, right? We know that the O's on the edges are not valid, in the sense that assuming we had another O here, right? Instead of an X, we had an O here, it would be at the edge, right? So if it's at the edge, then these O's are not completely surrounded by X's, right? Because then there will be an O that is at the edge. Okay, so the idea that should be given is that okay, that means if we figure out some sort of way to go around the edges of our board and then figure out all the O's, right? And let's say when we see all the O's on the edges, we change them to some sort of letter so that we essentially say, okay, you are not an O anymore and we are not interested in you. We change them into some sort of letter, let's say T, right? And then we'll run some sort of recursive call that checks the neighbors of this O, right? So in case we have like other O's connected to them, we are going to mark all of those ones as T, right? Because then they won't be valid. For instance, with the example I gave here, if we had an O here, right, and we went around our edges and we say, okay, this is an O around an edge and it is not valid, we know that running our recursive call, we are going to make all of these T's as well, right? And that is how we know that that region, well, it's not going to be valid and we can't turn it into X's, right? So just to recap, the approach we'll be using here is to go through the edges, right? And then when we see an O, for instance, in this case, we are going to turn it into like a T just temporarily. And then we are going to recursively run that function on its neighbors as well, and if there are O's, it's going to turn them into T's, right? So by the time we are done, in the instance of the image that we have here, by the time that we are done, let's say converting this to a T, we know when we are iterating through it later, this is not something we are even going to consider as an O. So as we iterate through our matrix, whenever we see an O, we know that that is an O that has to be surrounded by X's, right? It is an O that is valid enough to become a region, right? And that is how we are going to be able to determine the number of surrounded regions that we have in our given matrix. Once again, this is one of those questions where beyond understanding the logic, just merely past 50%, seeing the code brings more things into light. So let's just jump right to the code. Okay, so just before I start writing a code for it, I want to highlight that specifically for this question, we do not need to return anything, right? So based on whatever algorithm we write, what should happen is by the time we are done, all these regions, right, that we know are surrounded by X's, we just need to change them into X, right? So it's like there's a surrounded region, it's sort of like you've captured that region. At least that's how I like to think about it. And we don't have to return anything. We just need to make sure that all these like regions that are valid enough, they contain zeros and are surrounded by X's. That's what I mean by valid enough, and are not on the edge. We just write our algorithm so that it changes all those O's into X's, and then we can leave it there. All right, so to get started, one thing you notice with solving graph problems that are matrices is that you usually have to start off by defining like your rows and columns. It's almost like constant, at least with like most of the problems I've had to solve. So here that our rows is going to be equal to the length of the board, and our columns will be equal to the length of the board at 0, right? And even before I go further, I want to start off with like a very simple edge case, right? And what's that edge case? If not board, or if not board at 0, then we know we just want to return. There's no point to run any algorithm on it at all because the board is not valid. You can say if not board or not board at 0, we just want to return. Okay, going on. The next thing I want to write here on line 10 is something called directions. I'll explain a little bit more about what it does when I start writing the implementation for the DFS, but basically it's going to help us navigate the neighbors of whatever cell we are dealing with a little bit easier. Okay, now before we even start writing like the main DFS function, I mean that is trivial and different people can write it in different ways. I think it's quite important that we focus on like the body, what I would say is the body of the code, which is first of all like going through the edges of our board to find those O's that are obviously not valid because they are not completely surrounded by X's, just by virtue of the fact that they're on the edge, and then mark them as a T, right? So we'll start off with the rows. We say for R in range rows, we are going to write some sort of function, right? It's a DFS function, and it's going to take a row and column, right? And as I have written here, the function traversing on R and O for all the R's in the row will essentially cover the left border, right? Because we have our the rows are essentially like moving through the board but then going down, right? So if we keep our column at 0, then it's essentially going to traverse the left border right here. Okay, the next one we want to do is also to run that function that we are going to be writing a short bit, and this time making it so that the parameters are the R, which is going to keep changing, and calls at -1 or columns at -1. So that would traverse the right border, right? Because now instead of staying here, hopefully you can see what I'm doing with the diagram here. Instead of staying here on this side, now we are doing calls at -1 and changing the row. So it's going to just go down this path, right? So then we make sure that we are covering the right border as well. So hopefully you can already tell that the rest that we have to do are just the top and the bottom. So we'll say for C in range calls, want to run that function on 0 comma C. What is 0 comma C going to do? It's going to go through the top of the border. Why? Because we are going to maintain our row being 0, and we are just going to change columns. Now remember, columns is essentially like moving vertically. Okay, so as we keep changing the columns and maintaining our row at 0, that is going to cover the top part here. Okay, and hopefully you can tell already, but then the last one we are going to do will be the bottom part, and that will take rows at -1 and C, right? So this time our rows being -1 means we are at the bottom here on the diagram, and we are changing our column, so that is going to keep going from left to right on the bottom of the board here. Okay, so now I mean, we are going to write our DFS function later, but essentially what it's doing is that as we go through the edges of our board, when we see a 0, we are going to change it and mark it as a T, and if it's connected to any other 0, we are going to do the same thing as well, so that in the end what we are going to do, and that's what I'm about to write the code for, is that we will essentially just iterate through the whole matrix, and this time we are going to look, if we see an O, right, then we know that it is a valid O, right? And just to recap, with the example we have here, we know that this O is going to turn into a T, and it's not going to be able to affect these other O's because they are not connected at the top, at the right, to the left, and clearly not the bottom. So this is not going to be touched, and obviously from looking at it we can agree with the fact that this should be a valid region. So when we see our O later, after marking all these edge O's into T's, then we know that this is an area that can be captured or surrounded, so then we will turn them into X's, right? But then if we, as we iterate through it, we see anything that has been changed to a T, which would have been done by virtue of these function calls that we have here, then we know that is something that used to be an O, and we can just change it back into an O. So when we are done with our algorithm, you see the zeros that we have here would be turned to X's. This 0 become an X, this 0 becomes an X, it becomes an X, and here remember we had initially changed it into a T, but we'll just change it back into a 0, and then we are done. So that's what I'm about right now. This time we are iterating through the whole board, so we say for R in range rows, for C in range calls, we say if the board at R at C is equal to O, then we know that is valid, right, and can be captured or turned into an X. So then we just make that assignment and turn it into an X, right? However, if at that board we have it such that it is equal to a T, right, equality sign is equal to a T, then what we want to do is just change it back into the O, right? So the whole purpose of changing these edge zeros into T's is so that later as we are traversing over every cell, we can tell that, okay, you are either like bordered by an edge, or you are connected to an O that is bordered by an edge, right? So after doing that, we can just convert them back into the O's, right? And that'll be it. Remember, the question says we do not need to return anything right here. Okay, now back to writing the first search function that is essentially going to be given two parameters, our row and our column. And what it's going to do is, remember we are running that function specifically on the cells in our edges, and if we see anything that's a 0, we want to change it into a T. Okay, so call it the first search is taking R and C, and the first thing we want to do is to check the boundaries, right? Because for instance, when we run the function on O here, right, it's going to turn it into a t, and later we'll run recursively to do the same thing on its neighbors, x to the top, x to the right, to the bottom, and the down here. And obviously looking at the down here, that's out of bounds, so we need to write a condition for that. Okay, if it's out of bounds, we just want to return. All right, so we'll say if the men of R and C is less than 0, or R is equal to rows, or C is equal to calls, or our board at R at C is not equal to O. Now let me explain that a little bit. So like with the example we have here, back at the diagram, you see that we only want to turn the neighbors of this edge 0 into t if they are O's, right? We don't really care about the x's. So it is important that, like, when we run the recursive call, it is checking to make sure that they are O's. If they are x's, we do not care about them and we don't run the functions on them, right? So in that case, we'll just return. Okay, and then once the coordinates we have given into the function, our row and column, passes the condition, what we want to do is that at that position we just want to set it to a t. All right, and then we want to recursively run that function on its neighbors. The first search is like quite interesting in the sense that it almost follows this same like pattern. It's just about adapting the question to that particular pattern, and then you can usually get your solution. And then you see that more in the videos I'll be posting later. So now to recursively run the function on the adjacent cells, we are going to do that using our directions array. So we'll say for dr comma dc in directions. Okay, so what does that do? Let's go back to directions right here. Consider the first list that we have here. dr is going to correspond to 1 and dc is going to correspond to 0, right? We will say our row column is going to be equal to dr plus r, right, and dc plus c for the column. So what does that mean? Assuming we are at this position and we add our dr to that row, right, that is going to go down, right? We don't add the dc being added to the c0 in that circumstance, so nothing changes with the column, but the row is going to go down. So with our first list, what it does basically is after we add it to our given row and column, it checks the bottom of it. Hopefully you can see the trend. This, because it's subtracting, is going to check the top of it. This we do nothing to the row, but then we add to the column, so it's going to check the right of it. Likewise, this is going to check the left. I feel like this is a little bit easier to think through how to recursively run the function on its neighbors. So that's what we are doing here. So after doing that for all the directions, all we want to do is recursively run that run our DFS function on the neighbor. So we'll recursively run it on row and column, and then we are done. So let's see if that works. Okay, I did something silly, forgot how to spell here. Okay. All right, so we see that works. I'm going to quickly submit it. Okay, so we see that this solution works for this question. Okay, so let's discuss very quickly what the time and space complexity is going to be. So the DFS, or the border marking phase, potentially it visits every cell once if the board has many zeros, right? The second pass also processes each cell. Now, considering an m by n board, we will see that at most we would be visiting each cell just once, right? So then our time complexity mainly is concentrated in these lines, and that would denote that time complexity is O of m by n. How efficient we are going to be time wise will be dictated by the dimensions of the board. right? And looking at our space complexity, in the worst case scenario, the recursion could include every cell in the board, right? So we have to be thinking about the core stack that the DFS is going to be using. And in the worst case scenario, where we are visiting each of the cells, the time and the space complexity associated with that will also be m times n, because then we'll have to do that core stack for each of the cells as well. Thank you, and I hope you enjoyed this video. See you next time.